the Dijkstra algorithm for shortest path, and this is the shortcode for that. And the main idea here it is, so this is a kind of a greedy algorithm. It's greedy algorithm. This is a greedy algorithm. And what does mean greedy algorithm? I will explain to you. This is based on the greedy algorithm, right? We already talked about greedy algorithm, but this is our first time touch on the graph algorithm, which use the greedy greedy technique. So I want to draw a picture here. It's A, right? And this is the source. This is the source loads, right? This is Dijkstry corresponding to single source shortest path. And let's give you a simple graph. And here we talk about, let's use a directed and cyclic graph, right? And this cyclic graph, which do have a positive weight. Let's just say positive weight, right? It's another node. And then we go to here, right? And then so we go to this one. This is load is end load, right? This end load. So we want to check this is single source shortest path corresponding to from this single source S. S is a single source. We want to find the shortest path. Let's say this is A, this is B, this is C, this is D, right? We want to find shortest path from S to A, from S to B, and S to C, and S to D for every guy. Let's give the weight, right? There's no weight, doesn't make sense here. So let's say this is the 2. I make the weight as simple as I can. And then I want to make this one to be, let's say we still have this guy, right? This guy. And then let's say we make this one to be 5. And this one to be 1, this to be 1, this to be 1, right? And then we want to make this one to be 1. Complicated, right? So now we want to say what is the shortest path from S to A. This may or may not obvious, right? Let's say we have, in this case, let's see this is -1. And this also -1, right? We say, or in that case, let's say this is 2. It's okay. And let's make this one to be let's just use this one, right? So in that case, they do have a cycle, but there's no negative cycle. This is this one. So this is a cycle, right? This is a cycle, but there is no negative cycle. Here I want to put a 7 here, right? So I want to make it complicated. So S to A, you may say, seems like it's okay. S to B, so S to B, but S to B may go to from here, right? So which one is better, right? They have different paths can go to this side. So if I say, okay, I even make it complicated, I have this weight, I have this weight, right? So how it could be? So in that case, in this solution, it is greedy algorithm. Greedy algorithm corresponding to every time, since it's starting from S, every time I explore as the shortest edges. This is the first step neighborhood. I check the smallest one, and I use this one. Then I use this one to extend to explore the step 2 relationship. So you have a step 2 relationship here, right? Relationship here, and also have step 2 relationship here. And from here, you want to make sure, so this is the smallest one, you count. And then after that, it is, you continually, explore it out. You explore the third step third step neighborhood. And the third step neighborhood, you check who gave you the smallest value, right? Check this one, right? This is the third step. This is also third step. Then you check fifth step. And when you check fifth step, you make sure, so when you check you make sure this one could be the second step for this guy, right? The second step for this guy, right? You want to make sure every time we export out and use the smallest weight. And then so let's take a look at the code. Since you want to check the smallest edges, smallest edge weight, so intuitively they use the priority queue very obvious. So initialize, this is for relaxation. Initialize in relaxation, we have D as its source to every vortex equal to infinity, right? So the previous slides we showed. This is initialize step. And also we show the parent loads of each this one is equal to long, right? We use L to represent the long. Can you see? And then so after that it is S corresponding to what? S corresponding to what you already explored. That shortest path weight exploration. In the beginning, from S, right, you want to check the shortest path. In the beginning, which S is assigned to be empty set, empty connection, and then you put VG to Q. And what is VG? VG corresponding to all the vortex in the priority queue. And then if Q is not empty, you want to extract minimum 1. So when you push all the vortex into the queue, at the same time you put the weight in the queue, right? Corresponding in very beginning, each load here they have this is 0, right? And also S, I forgot to mention. So this S, D, S equal to 0. You put the weight put this distance from S, the shortest distance from S to this vortex to be in the weight load. In the very beginning, this one is infinity. This one also infinity, right? Because in very beginning, you think from the source load to every load, they take a big effort, right? And later you want to use relaxation to check, step 1 relationship, what is the best effort, best path weight, and step 2 relationship, what is the best weight, right? Best path weight. And so you explore in this way, you expand in this way, okay? And then so this reason, this is initialized step. And initialized step, you will see the graph like that. They have the vortex weight. This vortex weight used to represent the shortest distance from source to current vortex. And then so after that it is you extract, so in this loop, right? So in the corresponding to, you need to check every vortex, which is non-S vortex, because it's a single source from S to every other vortex, right? And then so you extract the minimum 1. So in this case, A has been extracted, right? A has been extracted. So S, which you have A is here, right? A is here. Can you see? A is here, right? This is the in. Okay, this is a specific web browser-based PowerPoint, so they changed the format a little bit. Okay, and then so you retrieve this A, right? Because A is the first step from S to every another guy. First step relationship. A is the best guy. A could be a contributor. So A put in the S, put in the what they count for the what they already explored, visited. And then so after that it is check for adjacent vortex of this U. And for example, you have adjacent this one is corresponding to the next step. The next step relation, right? You check next step neighborhood. So when you check next step neighborhood, you check here which is the C and D, right? So when you check this one, when you extract this one, when you extract this one, in that case, it is this. You check you check what they do have the secondary neighborhood will change this the distance, shortest distance from S to A or not, right? This step to do. So may cause. So may or may not. So in this case, if you do have the second step relationship, so in this case it is, so when you relax use the C and D, in this case, does it influence? So since you do not have a triangular inequality, right? So in that case, no, they will not influence. They will not influence what you have the weight here. This is 2 here, and then when you explode out, so this will be in this relaxation, this will be 1, this will be 7. Can you see that? This will be 7. And then so after that it is you check all the adjacent vortex, then you go back to here, and check the pick up another vortex. So now the weight you have is 2, 7, to -1 and 7, right? Can you see? You change the edge weight. So in that case, what you have, the priority Q has been already changed. And also when you take a look at this one, you use this priority Q, you didn't DQ, right? You didn't remove. You just use this priority Q to decide which vortex has the shortest path weight from S to itself. So then in that case, it is you find out the C which could be extracted, right? So you extract this one, and you have a -1 and 7 here. So C should be picked out. When you pick up the C, so you use the same procedure, check all the adjacent vortex in this C, and check the step 3 relationship, and check this V, can this V will change the shortest path on this C or not, right? And so in this case, you can take a look. When you take a look at the shortest path, and you may find out in this case, so you check from the 0 through 7, no, that is have 1, that's 8, right? So you will not change this weight. And then you check from B, in this case, go to here is 8. So in that case, this value will not be changed, right? And then so after that, it is you go back to here and pick up the lowest weight, except what you have this one, So you have 7, that is D. And from D, you explode out. All the previous what you change its value, they already show they have multiple steps. Then you want to check even another more steps. Does it influence the weight, the shortest path from this load to this load? Can you see that? So then you follow these steps, and this just give you the rough idea. And now let's take a look. We give you the shooter code, give you idea how it is exploit out, right? So the idea of this Dijkstra algorithm and corresponding to from the single source load, they want to check a single step relationship and then find the shortest path weight for the one node, right? And then explore this load one more time and check the adjacent vortex and use this vortex as the contributor to check if you introduce the adjacent nodes, does this weight from this source to this destination will be changed or not changed. And so if you change that, then in that case, next while loop, and they will pick up specific shortest path to explore next neighborhood and to say how it influence or not influence. This is a greedy algorithm based procedure. So now I want to go to the next one. Next one give you an example. This is the same as what we discussed. And so this is starting point, this is a source, and we want to check the relationship between the shortest path from S to every another guy. We initialize to be infinity, right? Because initialize that is unreachable. You assume it's unreachable. And then you explore the neighborhood relationship, and then you change this the distance on each load, right? The weight of each load here is what we put here as the distance from S to any vortex here, right? Can you see? Okay, and then so take a look. When you check for the from S here, you check all the neighborhood, right? And then so from this neighborhood, you use the relaxation corresponding to this is the relaxation here. I check for relaxation, right? Relaxation here corresponding to in very beginning. When you take a look, the D S to U, and this DS to U, because it's the S is the source. In this case there is no single. This is a single step relationship. So this will be equal to what? Equal to minimum of the previous one, right? SU S to S plus W S to U, right? This is corresponding to, in this case, you think about this is the shortest path with this one, right? From S to U, corresponding this guy, go to here. And or what you have the previous one as U, right? And the previous one is as U has been equal to infinity. And now, since this one, so they change to be 10. Same thing here, they change to be 5, right? And now let's take a look at next slides. The next slide, it is consider, so you pick up this guy, right? So you have a Q, let's say Q. Q is a priority Q. So priority Q, you have U, V, X, Y, and they have weight in the beginning and infinity, right? All of them are infinity. And then so, and once you check the first step, this change to be 10, and this change to be 5. First step, right? First step relation from S to this guy. And then you have this smallest guy. So the V, you pick up a V, right? You pick up V. And you pick up a V, you go to the for while loop, right? While loop 1. So while loop 1, so the X is removed, right? X removed from Q. And since X removed, you want to check all the next neighborhood. For example, in this next neighborhood will influence this shortest path or not, right? So in this case, you want to check this relationship. You have the next relationship. This is the next relationship, right? This is the first step relationship. This is the first step relationship, right? We want to check. And then so you pick up this one to check a second step relationship. Second step relationship. For every second step relationship, you want to check if what you have is D S X is equal to minimum, right? Minimum of D S adjacent. I use adjacent S X, right? To represent one of this guy, right? One of this guy. Can you see that? And plot, I think I'll move to the next slides. Yeah. And then this one plus what? Plus the weight. Plus the weight from what you have the X to, no, the weight from adjacent X to what you have the X here, right? Or you keep the same as what you have. I use this one to represent the previous version, right? Previous version, this new version, this old version. So for every guy, for example, you check this one, right? You check, if the weight from X You check this one, right? You check if U is involved. Go to the second step, relationship. Does this one better than what you have the previous shortest path? From here, if you consider second relationship, let's use a different color to represent the second step relationship. This is the second step. I need to use different color. This is the second step. Why I cannot change? This is second step relationship, right? I suppose can change. Good. So this is a second step relationship, right? Second step relationship from S to X. Can you see? We use the adjacent nodes as the interesting vertex and check does only this path exist or not exist. And especially we want to check this path, it is the shortest path or not. In this case, it's not the shortest path, right? Then you take a look at this one. You take a look from here, from this guy to here, right? You want to see that if this V is involved, will influence this one or not. But actually here, you cannot do that, right? Because this direction is different direction. And then after it is, you check this one, right? Check through this Y. And when you check this through Y, and so in the beginning, this is infinity, right? This is infinity. So in this case, you keep this one. Keep this one. And then so after it is, you go to the check. You check since V is gone. So V this is X. I think I write it down. It's not here, right? This is infinity. X is the 5. X is 5. So this one is picked up. Then you pick up the U, right? You go to the loop. So this loop finish. And then you go to the loop 2. And loop 2, you pick up the U, right? When you pick up U, you check next relationship. And so check labels. So the labels here. The labels here, this is the label. This is label of U, right? This is label of U. And only have these 2, right? And in such case, it is, you want to check. Okay, so now the U, it is removed, right? U is removed from the Q, right? And then when you check U, you check all the adjacent nodes. You check this guy, right? In the beginning here, this is 10, right? This is 10. It's 10. So when you check, now you check D, same thing here. You check DU is equal to minimum of the DS to adjacent or the adjacent U, and plus the weight of adjacent U. You can see this is the same as to U, right? So you can see follow the same procedure, or the previous one, or the previous DSU. Right? And then so you can see here, originally is 10. And when you take a look the contribution from X, so you can change this one to be 8. Change this one to be 8. Can you see? And then so after it is, you can consider the next one for this guy. And for this guy, the previous step, this step. In this step, when you consider the adjacent vertex here, you already change this one to be 14, right? The previous step in this one. In this one, we just give you example for the U as example, right? When you go to the V as example, initialize to be infinity, then you have from use X, from X go to the V. In that case, this should be 5 plus line equal to 14, right? This should be 14 here. And this one should be the 7, right? Because when you check from the S to this vertex, you use what you have this X as the middle point, and you say you can change this weight, right? And then so you continually check. After that is you check if this one, check and we go to the loop 2, right? This is just loop 1. We give you one example. Now I explain why this change to be infinity, why this one was also changed to be infinity, right? Because it's have multiple adjacent vortex. You have to take a look. And then so after that it is, once you check this one, you can want to take a look to say if you need to change the specific edge weight or not, based on the adjacent vortex, based on the involvement of adjacent vortex. I think this is we give this one as example, right? And so, okay, I think this is good, right? So this is infinity. First, it is infinity. This is why we use the previous example and show you that it's the same what we discussed. And then so the runtime analysis of Dajcik's algorithm, and from what we take a look at the code here, you see you have to take a look at every vortex and have to take a look at every edges, right? So in that case, this is the runtime here, which is corresponding to V plus E. This is also the initialize use the OV time, use the theta V time, and in the while loop they extract the minimum, which is the V. This should be log V, and then so decreased K for E times. So this is that's good, right? And such that the total time and corresponding to, since you need to have for every vortex you need to pick it up, right? So this is the V times, this is the OV plus log V plus E. And since you have adjacent, this is adjacent E, right? This is adjacent E. And then so use this one times all the V, right? So this is the runtime. Okay, and then so I think we finished the single source shortest path. Now let me know if you have any question. Do you have any question? So is clear or not clear?
Guys, you can use the yes button in the participants list.
Okay, so the previous one corresponding to single source shortest path, and in this one we use the greedy algorithm. And so now you can take a look at this code. Take a look at this code. And then corresponding to every time you extract the shortest path and the shortest path the weight. And then so you explore this vortex and to check the next neighborhood and to see this neighborhood relationship will change the shortest path from the single source to the previous vortex or not. Okay, so this is the greedy algorithm. Let me know if this is clear or not clear. I want to make sure you have question or no question, since this is remote session. Okay, I think seems there's no question, right? Or maybe okay. So let's take a look at the Bandikas and Bastion. Okay, let's take a look at this one, right? Even we do not need to go back to the slides. Let's take a look at go back to the last slides. We can use this one. Okay, so in this is for initialization step. In this initialization step, we need to have O V, right? And OV corresponding to number of vertices, because in this step, it is initialize all these arrays. Initialize the distance for every vertex from source, right? So this is, and initially this should be -1, but since we ignore the lower asymptotic order, so this is fine. So this is for this step, right? The first step need to take OV time, and this 2 is constant runtime. And then so for this one, this is go to the pickup vertex one by one. So corresponding to in this the whole loop here, we need to have an OV loops. This we need to have OV loops, right? And then so now check for this one. Let's check for this the third big step, right? This while loop. So while loop we have OV loops, and for each loop, extract minimum with how many? What is runtime? This is extract the minimum is upper bound by log V, right? Log V. Why? The reason it is you remove the O1 time, but you have to adjust the complete binary tree, and this is the log V. And then this is O1 time. And take a look at this one. This is for each V belong to adjacent U, right? So corresponding to check the edges of V. And so in this relaxation, they only need to have constant runtime. This is constant runtime for relaxation. So the for loop here, we only have needed time for what? For adjacent. This is runtime we need, adjacent U. And think about, take a look at the whole thing together, right? This is just what? Adjacent V, adjacent U. And this is each, we need to have extract every vertex. And think about, every vertex, you count the edges and adjacent edges. So it means if we take a look at the whole loop, while loop here, we need to have O1, OV time times O log V time, right? Plus, this one we can ignore because it's lowercase than this one. And the summation of adjacent of U among the odd U. What is equal to this one? It's equal to OE. Can you see? So this is OE. If you take a look at the textbook, you will find out this is the runtime. This runtime. Can you see that? This one, it is lower order. This is lower order. So finally, this is the runtime for this algorithm, which is this is runtime. This is runtime. Okay, so any more question? Thank you. And then so run Anir. So I think you may miss something. That'll be good. Take a look. For example, when we talk about the V, use this sign. When we talk about this one, this is corresponding to the number of vertices. And you may need to familiar with what is the vertex, what is vertices, what is this corresponding to. And they'll be better. You take a look at what will give you the web page, which include all the previous important concepts. Also have video there. For today's this one, I will try to check the quality of this video. If it's not good, I may record another one for you. Okay, so I will send the email to you. Okay, so any more question? That's good. Okay, just be aware of this greedy algorithm. So this is very typical greedy algorithm. Okay, so I think maybe that's all. And if you have a question, email to me or email to Melodia. I'm sorry, who is talking? Malojia, are you talking? Okay, nobody talk.
Yes, Professor.
You are talking? Okay, go ahead. Okay, then so if there's nothing important, and then left, then so we may just say bye here. And then so I was trying to give you this digest algorithm, this video we made, and then so after that it is Wednesday we'll finish the another algorithm, which it is the Bellman and Bellman's algorithm, and then so we go to the minimum spanning tree. Okay, and so we have 2.5 weeks left. So we expect to have one class in the April 29th. We expect to have one more class in the even in the April 29th. Just be aware that we have 2.5 weeks left. Okay, so thank you very much. Let me know if you have any question, and then so please reach to TAs, and they still have office hour. And then so I think I would like to draw a conclusion here, and I wish everybody have a great remaining of the day, and they stay safe and healthy, and enjoy the weather. This is good weather now, and also we pray everybody hope everything would be fine and it would be gone very soon. Okay, and then so let me and all our instruction team people know and your question. Okay, and for the rain and near, I will make another video for this tree for you. Just to make sure you need to take a look at the web pages. The another video is posted there. Okay, so that's all for the day. Thank you very much. And then so I have to stop sharing, and then have to exit this remote session. Okay, thank you very much. Okay, my friends, please take care. Okay, bye.